Hello everyone and welcome back to the class. Now we will study a new class of circuit which are formed by combination of passive elements and are known as RC circuits. So far we have studied passive elements like resistor, capacitor and inductor, also their behavior for DC sources, and their voltage current, current voltage and charge current relations. Now we will study a circuit which are formed by combination of these passive elements. First combination is of resistor and capacitor known as RC circuits, and the second one is resistor and inductor known as RL circuits. And this combination of RC or RL circuits have wide application in electronic systems, communication system and also in control systems. Like the analysis of resistive circuits, we have used Kirchhoff's laws, and again here we will use Kirchhoff's laws for the analysis of RC and RL circuits. As a result of applying Kirchhoff's laws on resistive circuit, you obtain algebraic equations, where if you apply Kirchhoff's laws to RC or RL circuit, you will get a differential equation. And these differential equations are of first order, and hence these RC and RL circuits are collectively known as first order circuits. And by definition, a first order circuit is characterized by a first order differential equation. Now we have two types of first order circuits which can be either RC circuit or RL circuits. And we have two ways through which we can excite these circuits. The first way is using initial condition of the storage element. This excitation method is also known as source-free circuits. In this we assume that energy is initially stored in the storage element, which can be either inductor or capacitor. And when these storage elements are connected to the resistor, the energy causes to flow in the circuit and gradually dissipated in the resistor. Although the source-free circuits are free of independent sources, but they may have dependent sources. And the second method through which we can excite these first order circuits is with the help of independent sources. And here in the first part of electric circuit course, we will use DC independent sources. And we know that for DC independent source, a capacitor acts as an open circuit where an inductor acts as a short circuit. So simply using the Kirchhoff laws, we can easily find the circuit variables. And now we will start the analysis of source-free RC circuit. And for this analysis, consider the given circuit in figure 1. The given circuit was earlier excited through an independent DC source, and this independent source has charged the capacitor of the given circuit. Now we will disconnect the DC source and the capacitor will release its energy to the resistor. Now we will make analysis of the given circuit when at sudden source is disconnected and energy from capacitor is released to the resistor. Here, a circuit response is a manner in which the given circuit reacts to an excitation. Now for source-free analysis of RC circuit given in figure 1, initially a DC source was connected and at sudden it was disconnected. So before the disconnection, the capacitor was initially charged. So the initial voltage stored in capacitor at time t equal to 0 will be V0, and the initial energy stored in capacitor will be half capacitance of capacitor product with V0 square. Now to find behavior of voltage, we will apply Kirchhoff's current law at the top node of the circuit, and will give us a relation of sum of current through capacitor and current through resistor will be equal to 0. And we know that the current through capacitor is equal to capacitance of capacitor product with rate of change of voltage, and current through resistor is equal to voltage across a resistor divided by resistance of resistor. Substituting these values, we will have an equation given at the end of the slide. Now by substituting the values of current through capacitor and current through resistor, and by rearranging, we will have an equation which will be rate of change of voltage plus voltage divided by RC equal to 0. And this is the first order differential equation because we have only one derivative, and that is of voltage. Now for solving purpose, we will rearrange the elements of the equation and will integrate the both sides, and the resultant equation will be natural log of voltage will be equal to the sum of minus 1 over RC t plus natural log of A. And here A is the integration constant and will represent the initial condition of the circuit. Now using the logarithmic properties, we will have the equation natural log of voltage over A will be equal to minus time t divided by RC. Now for the last equation obtained in the last slide, we will take power of exponential on both sides, which will give us voltage over A equals exponential with the power of minus t over RC. Or we can say that voltage V of t will be equal to A multiplied by exponential power minus t over RC. Now for initial conditions, we know that V0 is the only stored voltage in the capacitor. So A will be equal to V0 and hence V of t will be equal to V0 multiplied by exponential power minus t over RC. And from this we can say that the voltage response of an RC circuit is an exponential decay of the initial voltage, because exponential with negative power is a decaying function and its value will be decreased as time increases. So as capacitor will release its energy to the resistor, the initially stored voltage V0 across the capacitor will decrease exponentially. Since this response is due to energy stored in capacitor and depends on the physical characteristic of the circuit and not due to some external voltage or current sources, so this response is also known as natural response of the circuit. The natural response of a circuit refers to the behavior which can be in terms of voltages or currents of the circuit when no external source of excitation is applied. The natural response of any circuit depends on the nature of the circuit alone, which means with what component it is composed, and no external source will be present. In fact, in case of RC circuit has response because energy was initially stored in capacitor, and the natural response of voltage corresponding to equation obtained in the last slide is plotted in the figure 2. When time t equal to 0, the voltage is equal to V0, and as time t increases, the voltage decreases toward the 0. And the rate at which the voltage will be decreasing is expressed in terms of time constant and is denoted by tau, which is a lowercase Greek letter. Now the time constant is defined as time constant of a circuit is the time required for the response to decay to a factor of 1 over E or 36.8% of its initial value. Now from equation 3, replace the time by tau, which is the time constant of the circuit. We know that V of tau will be equal to 0.368 V0. And this can also be verified from the graph represented in figure 2, which shows the natural response of an RC circuit. Now in equation 1, the voltage will be equal to 0.368 V0 if time t equals to tau, and tau will have a value of RC. So in terms of time constant, equation 3 can be expressed as V of t will be equal to V0 exponential power minus t over tau. Now using equation 5, we will find various values of V of t over V0 in terms of time constant tau using the given relation and summarize the given values in table 1. From table 1 we know that after the time of 5 tau, the value of voltage is less than 1% of initial voltage V0. So we can say that the capacitor is fully discharged after a time of 5 time constant. Or we can say that the RC circuit takes the time of 5 tau to reach the final value when no changes take place. For every interval of tau, the voltage is reduced by 36.8% of its previous value, regardless the value of time. So if at current time t, voltage is V of t, at time V of t plus tau, which corresponds to next interval, its value will be V of t divided by E, or 0.368 multiplied by V of t. Now we will summarize few characteristics related to the value of time constant. Now from equation 4 we know that for a RC circuit, tau is equal to RC, and from equation 5 we observe that the smaller the time constant, the more rapidly voltage decreases and the response of the circuit is quite faster. Now any circuit with small time constant gives a fast response in that it reaches to its final value very quickly due to quick dissipation of stored energy. And a circuit with large time constant gives a slow response because it takes longer to reach the steady state. Now whether the time constant is small or large, whatever the rate is, the circuit reaches to its steady state or the final value in the 5 time constants. Here steady state means the final value of the response. Now the graph given in figure 3 represents various responses for a circuit with different time constants. When time constant is small, let's say equal to 0.5, the response quickly reaches to 0 or its final value, or when the time constant is equal to 1, the response is a bit slower, or when time constant tau is equal to 2, the graph reaches to its final value more slowly. Now from previously obtained relation for voltage V of t, current through the resistor, which is equal to voltage V of t divided by resistance of resistor, substituting the values of V of t, the current will be equal to V0 over R exponential power minus t divided by tau. And the power dissipated in the resistor will be equal to the product of voltage across resistor and current passing through resistor will be V0 square divided by R exponential power minus 2t divided by tau. Now assume that the DC source was disconnected at time t equal to 0. Now from time t equal to 0 to present time t, the energy absorbed by a resistor will be equal to the integral of power from time t equal to 0 to present time t. Now substituting the value of power and taking the constant out of integral and integrating the time from t equal to 0 to present time t, we will have a relation of half CV0 square into 1 minus exponential power minus 2t divided by tau, where tau is equal to RC. And here for integration purpose, the integration variable is changed from time t to lambda. Now for any source-free RC circuit, you have to keep two things in mind. First one is to note down initial voltage V0 across the capacitor and the time constant tau of the circuit. With these two quantities, you can obtain the voltage across capacitor V of t, which will be equal to V0 product with exponential power minus t over tau. And once you know the capacitor voltage, then you can easily find the other circuit variables like current through resistor, voltage across resistor, and current through capacitor. Whenever the circuit have single capacitor, several resistor, and dependent sources, and you have to perform source-free RC analysis. And for this purpose, you can use Thevenin equivalent circuit, and the capacitor will act as a load, and you can find the Thevenin equivalent at the terminals of the capacitor. And with Thevenin equivalent resistance connected with capacitor, you can form a simple RC circuit. Now in finding the time constant, the R will be referred as Thevenin equivalent resistance at the terminals of capacitor, and we take out capacitor and find R. Now in the given example for the circuit in figure 4, the initial value of voltage across capacitor is 15 volt. As the capacitor starts releasing its energy, you have to find capacitor voltage, voltage across 12 ohm resistor, and current through the 12 ohm resistor when time t is greater than 0. And if you analyze the circuit, the given circuit have 3 resistors and 1 capacitor. And this doesn't conform with the standard RC circuit. Now in order to change into a simple RC circuit, we will find the Thevenin equivalent circuit at the terminals of capacitor. And with this Thevenin equivalent resistance, we will transform our given circuit into a simple RC circuit. Once we have the relation for voltage across capacitor, then we can easily determine other required variables Vx and Ix. Now for Thevenin equivalent resistance, we will remove the capacitor, and in the remaining circuit, we will have a 8 ohm resistor in series with a 12 ohm resistor, which will give an equivalent of 20 ohm resistor. and this 20 ohm resistor will be in parallel with a 5 ohm resistor. Now solving using parallel form, the equivalent resistance will be equal to 4 ohms, and the circuit is shown in the figure 5. Now the equivalent circuit is shown in the figure 6, which is analogous to figure 1. Hence the time constant will be equal to R equivalent product with capacitance of capacitor and will have a value of 0.4 seconds. And the voltage V of t will be equal to V naught multiplied by exponential power minus t over tau. Substituting the value of initial voltage stored and time constant tau, we will have voltage across capacitor will be equal to 15 into exponential power minus 2.5 t, and this voltage across capacitor is equal to V of t. Now using the voltage division, we can find the value of Vx, which will be 12 divided by 12 plus 8 in product with voltage V, and this will have a value of 9 into exponential power minus 2.5 t volts. And the current passing through the 12 ohm resistor will be equal to voltage of resistor divided by 12, and this will be equal to 0.75 in product with exponential power minus 2.5 t amperes. Now in the next example, for the circuit in figure 7, have a switch which was closed for a long time and is opened at time t equal to 0. Now you have to calculate energy stored in the capacitor. Now we will start the solution. For time t less than 0, the switch was closed, and during this time the capacitor will act as an open circuit to DC as shown in the figure 8. As capacitor will act as an open circuit, so the voltage across capacitor will be equal to the voltage across 9 ohm resistor. Now with the help of voltage division rule, the voltage across 9 ohm resistor will be equal to of 15 volt when switch was closed. And we know that the voltage across capacitor cannot change instantaneously, so the voltage across capacitor when the switch was closed will be equal to the initial voltage or the voltage at time t equal to 0. So V naught will be equal to 15 volt. Now for time t greater than 0, the switch will be opened and the resultant RC circuit is shown in the figure 8. The RC circuit in figure 8 is source free. The initial voltage stored in capacitor is due to the independent source present in figure 6 when switch was closed, and the same source has provided initial energy to the capacitor. Now we will start analysis of source free RC circuit. When switch turns open, the 1 ohm resistor and the 9 ohm resistor in figure 8 both are in series, which will give an equivalent of 10 ohm resistor. So the time constant for this RC circuit will be of R equivalent into capacitance of capacitor will have a value of 0.2 seconds. Now the voltage across capacitor for time t greater or equal to 0 will be V of t equals V of 0 multiplied by exponential power minus t over tau, and will have a value of 15 into exponential power minus t divided by 0.2, or 15 into exponential power minus 5t. Now the initial energy stored in the capacitor will be equal to half capacitance of capacitor multiplied by square of initial voltage stored in capacitor, and will have a value of 2.25 joules. And thanks for watching this video.